Hello, everyone. You're all most welcome to this webinar, third in the series on paper conservation. We'll be starting at around 11:30, so by that time we can introduce ourselves and chat among ourselves. You can unmute and talk. This is a Zoom webinar, and we have a question answer icon over here. If you have any questions from the presentation, you can always put that question in that question answer icon. You can click on the icon and type the question over there. So it's 11:30 and we'll start our discussion on microenvironment in museums, and specifically because the series is regarding paper conservation, so we'll focus more on the paper objects. So I'll just start sharing my screen. And I hope I am audible to all of you. You can just tell me in the chat. Okay, so today we'll be talking about the microenvironment. And before we go into the technicalities on our why and how of the microenvironment, I would like to explain the term microclimate or microenvironment. It is the climate or environment of a small specific place within an area as contrasted with the climate of the entire area. So for museums, airtight cases and special storage rooms are created that regulate the climate in a specific volume around the artifacts. So we create a microenvironment kind of thing in museums, in display cases and in storage rooms or cabinets and all. Now, exploring the microenvironment of some ordinary display case, let's see this in this picture, a very ordinary kind of display case is shown, and we'll just try to understand why we need to talk about microenvironment. If you have a very close look at this picture, you'll see that there's a stagnant air inside, and even the heat, because this particular museum has no air conditioning, and a lot of natural light comes in through various windows and other sources. So whatever light is, we know the greenhouse effect in glass. So whatever light rays go inside the display case, they're trapped inside, they can't come out. And plus, if we have a very closer look, I'll show in the next slide, we'll see that there are gaps. This is not properly sealed. So there are gaps in the glasses, and the dust which is entering the display case has no way to come out. So we can see in such display cases, we have stagnant air, trapped dust, heat, and humidity, and also spores of microorganisms. So that is why we need to look into this microenvironment created in the display cases or storage areas or painting frames. And because this can be damaging for the artifact or a paper or archival material. This is the close up of the same display case, and we can see, I'll try to, we can see the gap in the glass, and which is really dangerous because the dust can also enter and settle on the textile which is displayed in this particular display case. Now, before we talk about other things, like the reasons of for studying the microenvironment and how we can control or regulate the microenvironment, we need to understand a few terms. I would like to all of you to recall what we studied in physics in our school or high school. Uh, if you remember, we talked about system and surroundings. And even if you don't know about that, I'll just explain it here. So whenever we are talking about the exchange of energy or matter, we talk about a system and all the things around surrounding it in the universe. So here, the system that we are talking about is the painting frame, display case, a storage room or cabinet, and the surroundings are the outside environment, maybe the environment of the building in which it is placed or the room in which it is placed. So the surroundings, the environment of the surrounding is the normal environment that we'll just call it environment, and the environment inside this system that we are studying would be called the microenvironment. Now here again, I would like to elaborate that system is the part of the universe that is being studied. Here it can be a framed painting, a display case, or a room and or a cabinet. And the surroundings are rest of the universe that interacts with the system. So a system, as we studied in our physics and its surroundings, can be as large as a rainforest if we are talking about, if we are studying the rainforests in South America, or as small as the contents of a beaker in chemistry laboratory. Now, getting it a better picture of what we are talking about, the yellow spheres here represent a system we are studying. It can be a display case, it can be a painting, or a frame, or a box, or a storage cabinet. And the blue arrows are the exchange that is taking place. Here we are talking about two kinds of exchange of matter, material particles, and exchange of energy. Now, there are three kinds of systems that are studied in physics or science: open system, closed system, and isolated system. In open system, both matter as well as energy can be exchanged with the environment, with its surroundings. In a closed system, matter cannot be exchanged because it is very tightly sealed, but the energy can still be exchanged. And like in display case, at least the light is entering the display case, and that is required also. If we stop that also, if there is no exchange of energy also, then the system is called isolated system. So here we will be mainly focusing, we don't need to talk about isolated system, we will be talking about open system and closed system. So we need a closed system for our display cases. And now, if we talk about this more in relevance with what we are studying, the museums or the paper conservation or the display cases or the cabinets, then the matter that we are more interested in that is being exchanged with that system and the surroundings is dust, microorganisms, the microbial spores, gases, and humidity. And the energy that we'll be talking about is light and heat, which heat might cause temperature change, and we need light rather. So we want the light to pass through from the surroundings to the system. But of course, we can choose a light source which is less damaging to the object, which is not damaging to the objects. So the source of light is important, but it has to be transferred to the exchange, has to exchange with the surrounding. So we'll take one by one. We'll be talking about the system's microenvironment and how it is required or not required in certain cases. And we'll also talk about the various things, the dust, microbial spores, gases, humidity, light and heat. Won't be discussed as much as the first 4 points. I'm saying that we'll talk about like why this exchange of matter or energy is of course being transferred, but even matter, if it is transferred from the environment, the surroundings to the system's microenvironment, is okay in certain cases because since last many decades, you can say we are using HVAC system in the buildings, which is taking care of not just the temperature as in the ACs or air conditioning devices, it is also taking care of the dust particles and the spores and the overall health of the air. So if the building is using HVAC system, uh, it won't need, it would just need very little protection for objects on display, just like the dust won't be there, the people shouldn't touch the object, and that is it. So there was, we'll be talking about this in later slides. Now, talking about the system can be a frame in this particular case of our discussion, or it can be a display case or a storage area. Now, damaging factors in the environment. I'm just mentioning all those 4 that I've already mentioned. The dust. Dust is composed of particles with a diameter of approximately 2 micrometer or higher, which comes from soil or animal or vegetable residue. And why dust is dangerous or damaging to our objects? Because it can cause, it facilitates rather water condensation on objects and also the biological attack. Secondly, spores of microorganisms. We have studied in all these years of this research, and we have studied so many papers that come in our journals and all, the microspora of various museum environment and all. And what we have found is that many fungi and bacteria produce serious damage in historical materials, which are decomposed from the impact of specific enzymes. Like we talked in our earlier webinars also about the cellulases. There are some cellulose-loving fungi and bacteria, then proteases. And since they do not eat the food, they have extracellular digestion, they release the enzymes, and the material is digested outside their body and then they absorb it. So all the impact of all these enzymes that they secrete wherever they are, the enzymes can be cellulases, proteases, lignases, and organic acids. And the pigmentation and physical damage in the material are also deleterious. They also have a damaging effect in addition to the biodeterioration. Now, fungi are particularly dangerous because they show a substantial tolerance to environmental conditions. In addition, they require lower relative humidity than bacteria for their development and produce spores that are easily dispersed by moving air. Now, here we have to understand this that when we look into the library archival material, the paper objects in museums and archival material, um, we mainly find the fungal damage, and there is very less biological damage. So this is the reason, because they require very low humidity, means if they don't require like saturation point or something, even at 70%, 65%, if the environment is stagnant, they might grow. So this is dangerous. And dispersion of spores in many is the main cause of contamination in environment. The spores produce allergies to people and biodistribution in the historical objects. And as I was talking about, it was the next slide. We have done so much of research in all these decades, and now we know that which main species are always there in the environment, even inside the buildings, historical buildings or archives or the museums. And some of these rather I have identified myself in my dissertation of masters. Alternaria alternata was there, Aspergillus niger was there, Cladosporium herbarium, and Penicillium communae, Penicillium notatum, Trichoderma I had also found, and Gliocladium I haven't um, seen in my studies. And the genera, these are the species. Then genera, the main genera that are found in the air, in the buildings, in the inside environment are Aspergillus, Penicillium, and Cladosporium. They're the highest number of viable colonies in indoor environments. Then Mucor and Rhizopus are zygomycetes that have been found mainly on surface samples. Rhizopus, a soil fungus, has been detected in surface samples of from objects with dust accumulation. So here the dust also is playing the role in the damage. Now, the bacteria isolated from air and paper samples include the genera Bacillus, Bacteroides, Pseudomonas, Micrococcus, Streptococcus, Streptomyces, Staphylococcus. Now, actinomyces strains have commonly been detected in both air and surface samples. Next point is of humidity. This is something very important. If we control the humidity to a very acceptable level, then even fungi won't grow in that microenvironment. Now, relative humidity inside the display case varies depending on the rate of air exchange between the inside and outside, which may occur through one of the following processes. Now, the three processes are diffusion through the porous structure of the material used in the case construction. Number two is the airflow caused by the variations in the temperature and pressure. So because air would move from a high pressure area to low pressure area. And the third is the convective airflow. So because of this airflow, the humidity would vary. Like we saw in the earlier picture, the close-up that we saw in the second or third slide, there was a little gap. So there is a continuous exchange of air. And but in airtight cases, or when we are controlling, we'll see in the later uh, discussion that the whole environment is controlled inside the display case, we actually allow at times little airflow, but that is just like one airflow, one exchange of airflow once a day or something like that. So, but when it is not controlled, then there is no, we don't know how much air is being exchanged in a day. So because of this diffusion through the porous material of which the display case is made, or the airflow caused by the variations in the temperature and pressure and convective airflow, the humidity changes. And this is the result. This is a close-up of, if you see display case in the bottom right picture. This is a display case from a museum. Though I think it has now been changed, taken away because it was really deteriorating badly. If you see uh, the back wall of this display case, it is covered with a fabric, and the fabric has got these fox marks. They were very prominent. They are not easily seen in the picture, but in the close-up, I have specially cropped the picture to show you the actual damage. These are other examples, like this is a paper manuscript on the top left, and you can see the waviness that has come because of the humidity variations. And the display case is not completely airtight. We can easily see the dust deposited on the stand and even the corners. And in the right picture, you see the termite, tunnels made by the termite. This is actually a storage area of a museum. So in the hot and humid climate like ours, um, this is very common. And I have received two such cases where in one of them, I have actually worked with them and taught them, their team, the anoxia treatment and the microenvironment control and everything. So their objects are now safely stored in a different storage area. This is another picture that we saw in our earlier webinar also. Um, this is a framed picture and it has got this fungus mainly because the backing, the microenvironment is not good. It is not controlling the humidity, and the humidity is trapped in the front behind the glass. So it's a very good kind of environment for fungi to grow. Apart from dust, spores, humidity, we also have internally generated pollution. The sealed boxes allow the creation of a microclimate which is independent of the surrounding room and which can be suited to the individual requirements of the specific artifact. However, this construction promotes the accumulation of airborne pollutants. Now, we might have sealed boxes. We might create sealed boxes with a particular microenvironment, like humidity we have managed with some buffering material, and the temperature we have managed. Um, but it might be very suitable for the individual requirement of that particular artifact. But uh, this kind of construction may also promote the accumulation of airborne pollutants because there is no ventilation, they can't move out, and they are being created inside. Maybe because the wood that is used to create that cabinet or the display case is of that quality, or any wood, actually, all the wood, they release the VOCs, the volatile organic compounds. Now, now we'll see how we can manage these different systems to avoid the damage because of all the factors that we have just mentioned. And we'll take one by one. We'll start from the smallest, the frame box. And rather, I wanted to prepare more on this. I don't know if the time will allow or not. Um, we have very interesting kind of boxes and frames created for, especially for panel paintings, because they're made of wood. Not exactly same, but quite similar we can create for the paper paintings also. I'll show you how if we don't do that, how paper paintings can be damaged within the museum like environment. And the second, we'll talk about the display cases, and third would be about the room or the bigger area or the cabinets. So frame, display case, and storage. Starting from the frame. Ideal microenvironment of a painting can be achieved by one of the following methods. There are three pictures. You can see three rectangular. This is, you can say, the cross section of the system of the frame or the painting. Um, in the first one, you'll see, yeah, There are two lines. One is black. This is the black thing is actually the painting that we want to preserve. Here we have another rectangle which is gray in color. This is the barrier. I should have marked these. This is the buffer. Just, I'm so sorry, it's not written properly. So this is the buffer, and so we can have a system to preserve painting. We can have a microenvironment where we have a painting and a buffer material enclosed in that microenvironment, the framing box. Or what we can do is we can just have a painting. There's no buffer material, but the frame itself or the box itself is acting like a buffer. It is expanding and contracting with the changes in environment and preventing the painting from undergoing those changes. And the third is that we can introduce some inert gas, some buffering material in the form of a gas in that box or the frame or the microenvironment of the painting. So let's see what we can do. Uh, I'll try to find out the pictures on my system and show you in a little while. These are more simplified representations of the three systems, the three framing systems. But if you see the actual pictures, maybe it would be better understood. But in any way, I'll just explain it again. Once again, I'll say that the painting with a buffer material, painting without any buffer, the frame or the box itself is acting as the buffer or um, uh, the regulating material. And third is we can introduce some gaseous inert gas. Now, what are the buffers? To understand the earlier representations, we need to know what are buffers. Buffers are additives to the microclimate's box that control humidity within the box or the frame, because the frame can be in the form of a box at the back. Now, examples are salts, magnesium nitrate, hexahydrate, silica gel, Artsorb. Artsorb is the commercial name, and it is similar to silica, silicon, and there's some lithium chloride, some salt added to it. Then zeolite, nickel pellets, nitrogen gas. Now, talking about the display case. Now, display cases, we'll talk about how microenvironment is controlled in different ways. The first is the ventilated cases. As I mentioned earlier, in some buildings, they are using HVAC control. So the environment within the building is all clean of dust and spores, and temperature is regulated, humidity is regulated. So artifact won't need any more protection except from maybe little dust or touch when the visitors are moving in. And rather, many display cases in the last century were designed to encourage the inflow of conditioned room air. This I would like to emphasize on the fact that it is not the kind of inflow that we saw in an earlier slide where there was a little gap in the glasses. So these are designed in a way that there is a movement inflow of air from outside to inside and from inside to outside of the display case. But it is not just like any gap in the manufacturing of the display case. It has to be properly designed. But in this scenario also, we'll see that air-conditioned museums were in minority, first of all, and in these museums, very limited range of environmental conditions could be maintained in each gallery, as some artifacts needed very particular and different conditions for safe display. a leaky or ventilated case might not be suitable. So specialized microclimate enclosures would still be needed. Here, I would like to give an example of, say, um, maybe there are some objects which are taken out from while digging in an archaeological excavation, and they are accustomed to the environment under the earth. So, what they'll require is they'll require a low temperature and high humidity, because if you take them out and put them in a outside environment, it would be a kind of shock treatment for them. So they have to be kept in a similar kind of environment from which they were excavated. So that kind of environment may not be in these HVAC controlled buildings also. So some specific objects have specific needs. So again, the microclimate enclosures need to be designed as per the requirement of the object. So there were ventilated cases designed to encourage the inflow in case of HVAC controlled buildings. But again, in those cases also, some of the artifacts might need very different conditions from what is required for the visitor comfort. Second kind of display case is self-buffering cases, as we mentioned in case of frames also. So the case is made of material which is self-buffering. They don't need an additional buffer or a control. In some circumstances, the materials and design of an enclosure create a self-buffering microclimate. The moisture exchange between the air trapped in the enclosure and the hygroscopic material remains balanced. So this is more common where the ratio of volume of air to the buffering object is relatively small. So if there's a small enclosure and this is the case and it is acting as a self buffer, this and the volume of the air inside, the ratio is nearly same, it is very small, then means there's not a big, like if the enclosure is huge display case, this is made of some self buffering material. Here the air inside is much more than the self-buffering case material. So here it won't be able to function properly. So if this is suitable for only those display cases where the ratio between the volume of the air to the buffering objects is relatively small. Third is the passive humidity control. So first we saw that case where there's no control, there's just, it is designed to allow the inflow of air with the surroundings because the building itself is controlled by HVAC system. And the second we saw that the control is done by the material of the case itself. And third, we are talking about, we are adding something, but it is not actively controlled. It is a passive control and mainly of humidity. Because if humidity is controlled, the microorganisms and other things would also be controlled. And dust, of course, because when we are talking about the control of a microenvironment, we want we want, whether it is passive or active, we want airtight display cases or the containers or cabinets. So this is about display cases. So passive humidity control, let's see. If it has to be well sealed, so dust is of course taken care of. This rectangle above, this bluish rectangle, is representing a display case. We can put something, a little tray or device in beneath the display case. Now this display case can be too high also, a huge one or a small one of a table size. Here we have kept a pull-out tray where we can introduce some buffering material. Buffering material I have already talked about briefly in the frame. They can be salts, silica gel, it can be adsorb, or nica pellets, or some humidity buffering paper, honeycomb panels made of humidity buffering. There are different kinds of um, buffering material. But here there's a tray, so we can add adsorb cassette or the gels in this. So when the air is moving inside, uh, because of convection, it is just passing through this material and being dehumidified or humidified. Uh, because here we'll also we have to keep in mind that this material, like silica gel and even the adsorb, they keep a check on a range of the humidity. If humidity is less, then they release it in the environment. If it is more, they absorb it. And we have to remember that this silica gel we are talking about is different from the silica gel that we see in pouches and when we buy some bottles or bags or something. That silica gel is just absorbs the water or humidity. It doesn't release it. So but the silica gel that we'll be using, it has both the properties. It can release as well as absorb the humidity. Now this setup can be improved if we add a little fan. It will increase the airflow and the frequency with which the humidity is being controlled in the display case. And we can also add a filtering unit to this setup to filter off the air of any unwanted particles or impurities. So this is all about the passive. This is still passive. It is not an active control where we know exactly that this is the humidity we want, and if it is any uh, greater than this range or less than this range, then it has to be controlled immediately, and the environment should always remain at that humidity and temperature and the air quality within the display case, not the building I'm talking about. Specifications for that particular artifact. Now, this was about the passive. Now, coming to the active microenvironment control in display cases. We are talking about display cases now. So, active climate control system will automatically identify the preset humidity value and actively dehumidify or humidify to maintain humidity within the preset range. The air um, positive pressure function of the system will stop air pollutants at the external atmosphere to enter into the display case of the museum display cases. Um, Display space of the, let me explain this. Suppose this is the environment of this is the display space of the display case inside this rectangle. So there is positive air pressure, which there's a pressure around, there's a positive air pressure of the system, which will stop because the pressure is outside. It will stop any air pollutants at the external environment to enter the display case. So a positive air pressure is maintained in the system of the display case, the display space of the museum display case. So this is done in case of active microenvironment control. This can be done in active microenvironment control only. The sensors within the display space will real-timely monitor both temperature and relative humidity and will keep continuous communication with the climate system after the preferred climate value is preset well. So there are sensors within the display case um, which are monitoring both temperature and relative humidity, and they're keeping a continuous communication with climate system after the preferred climate value is preset. And when the monitored RH value deviates from the preset one, the dehumidification by condensing or humidification by evaporation will immediately be immediately activated automatically. These are some examples where the paper manuscripts are displayed, books or paper manuscripts are displayed, and both of them are controlling the environment within this glass enclosure, within this display case, is being actively controlled. And how is it being done? Because we can't see any instrument or anything in the setup, but they have. If you see the platform at which on which these paper objects are kept, uh, it can be lifted up and some devices are installed inside. In this case also, some devices are being installed inside underneath this display. So we have talked about the humidity and temperature, how they can be actively controlled, but that is not all. Maybe certain objects are very important, and they need very stringent kind of requirements. So to meet those more stringent conservation requirements, we'll see that display cases can be fitted with microclimate and atmospheric control module. The protection modules can include a protective or inert atmosphere like of nitrogen. So generator that produces highly pure nitrogen through a molecular sieve system. There's a molecular sieve, so air passes through it and only nitrogen is going through it. And so the special atmosphere, what does it give to us? What does it provide? It preserves objects from aging due to presence of oxygen in the ambient air. So there's no oxygen, so no oxidation happening. Filters out all atmospheric pollutants, prevents onset of oxidation, and protect, because in certain cases it is just the beginning of oxidation that might start a chain reaction kind of thing and accelerate the oxidation further. So, and protects objects from pests and inhibits proliferation of aerobic bacteria, the bacteria which grow in, which need oxygen for their survival. And it is an ideal solution for preserving organic materials such as mummies also. So paper is an organic material. So this kind of environment we can create where even bacteria cannot grow. Now, what some of these microenvironment control systems and display cases offer? They can give a nitrogen environment, they can control the relative humidity and the temperature, the general kind of actively controlled display cases. And what are the benefits? Since there is no oxygen, no insects, pests, or germs, not even aerobic bacteria, no dust and no concentration of pollutants, and constant relative humidity, constant temperature, acid and germ-free environment. This is another example where a system, a microclimate generator, these are some brands, big brands which are creating such display cases and even the storage areas. And this particular microclimate generator is here and it has got a 3-wall system, and they can be controlling the environment of not just one display case but of many display cases which require similar kind of conditions, similar temperature and humidity conditions. So climate is created outside and it flows through these and through these walls. These are shut off walls if we want to stop this particular system. And one single microclimate generator can also regulate actively the microenvironment of many display cases. Now coming to the storage conditions. Now this is one of the examples where we rescued a large collection from a storage room, which had this termite attack, and this collection was very important for a particular community. So it was taken out from there, and they created a special storage um, area, room rather. Now they have three such rooms in which the temperature, humidity, everything is controlled. And apart from that, they have put all their important documents and paper and textile objects in separate bags. Um, Created by Anoxia treatment. So they have a special plastic. We'll talk about that in a short while. That it's not a normal plastic, which is just heat sealed and oxygen taken out of it. The material itself is very different from normal plastic bags that we use. So one thing is that the microenvironment or the environment of that room is controlled, and the microenvironment of each and every bag is also controlled. So we'll see how we can do that. We can do, of course, we can control the microenvironment of the whole room. This is, or the cabinets. This is being done by certain brands which are already working and manufacturing these kinds of display cases and cabinets and other things. But apart from that, what we can do is we can also store objects separately in an anoxic environment if they are very important, and if we think that they can be easily damaged by some biological attack or even oxidation. So anoxia is basically atmospheres with low concentration of oxygen. So we are creating a microenvironment with very low concentration of oxygen. Rather, we are trying to have no oxygen at all, but we we can't avoid certain leakages and all. So whatever, even with the leakages, we have um, managed to put something, some material which will absorb whatever oxygen has might leak in. Um, so we are saying that atmospheres with low concentration of oxygen. So why we need this anoxia? Basically to prevent biodeterioration and to prevent deterioration related to oxidation. And practical experience has shown that conventional fumigants, now when these objects, in this particular case I'm talking about, they were in the earlier storage room, there was a lot of insect attack, there was termite attack. So before we take them to any other storage facility, we need to treat them. So if the biodeterioration has already started, then also for the treatment, we generally use fumigants that can have adverse effect on various materials, as well as they are damaging to the staff also, the person, they pose threat to human health and must be applied by trained personals or contracted to some specialized pest control operators. So in any case, they are damaging to environment, health, and objects also. So they can also be treated, the objects which have got damaged because of they have got insects or there are various stages of those insects inside them. They can get we can get rid of the whole biological population in the collection by anoxia itself. So anoxia is quite safe for environment and people who are handling the objects and doing performing this particular process. Now, history of use, when did it come into use, especially in conservation? So, in food industry, it was always there. Atmospheres with low concentration of oxygen had been used for the control of pests in stored food products for several decades before this method was adapted to the treatment of museum artifacts in late 1980s. The considerable research on the efficiency of modified atmosphere for the control of pests in the stored food has been conducted since about 1970s. But if we talk about the museums and storage facilities and archives, the oxygen-free display and storage of museum objects is still complex and is rarely used. Rather, I'm always talking about this particular thing because I think it is always better to be preventive, to avoid any biological attack. And if in a microenvironment there is no oxygen, there won't be any biological attack because any apart from anaerobic bacteria or microorganisms, all the organisms need oxygen to survive. So it is very safe and it should be used more frequently through in the museum world and the archival world also. So we'll see how we have done this, and it is done in many archives, libraries, and all. This kind of setup can be reusable also, means bubble can be created maybe just for once, or it can be we can create a bubble and put the objects in it and take the objects out and use the same bubble for other objects also. So it is reusable also, and I think it should not be, if we buy this setup, I think it is quite costly right now, but if we do it on individual objects and we know the material and how to do it, it won't be, I think it's not that costly. So methods and materials for anoxia of insects in museum objects or even the paper objects. Here I'll be putting some paper and textile objects in a bag, and I'll just take one by one what all is required. I wanted to show you this picture first, but I think it is at the end of this particular section. Because I'll just, in the small picture only, I'll just explain. This is the heat seal machine. There's a bag. This is Y hose, which is introducing nitrogen and taking out all the air. And in this, I'll show you in the next slide, maybe a slide later, that there's a small sachets of oxygen scavengers. So let's see. So I have a raised hand over here, but I don't know how to go about it. So let me see. So I'll answer later. First of all, talking about that enclosure, the polythene, the plastic kind of thing that we see for anoxia in storage or for treatment. The container and the method. So the container can be, in the earlier slides you have seen two pictures. It can be a huge one or it can be a small one just for a little object. But the material is same, the plastic is same. And it has these 5 layers. This one is showing 5 layers, but we need at least 3 layers in this particular anoxia treatment. The inner layer is the sealing film, and the middle layer is the oxygen barriers from which no oxygen can pass through. And the third or the top layer is is to prevent the oxygen barrier layer, so that there's no, if there is some kind of tear or something has crashed through it, it is not damaging directly the oxygen barrier. So though it doesn't look like 3 or 5 layered film, it looks like any other plastic or polythene. You can't make out the different layers. Secondly, we need an oxygen scavengers. Some sachets, various sachets are are available in the market. These are oxygen absorbers. Basically, they have iron Now, oxygen scavengers or oxygen absorbers are added to this whatever enclosure we have, whether a big one or a small one, and the quantity would depend on the volume of the air inside. So we have specific formulae for that. I won't go into details about those in this particular discussion. Um, so the amount of these scavengers depends on the amount of air inside that enclosure. So they are added to the enclosure packaging to help remove or decrease the level of oxygen in the package. They are used to help maintain product safety and extend shelf life. There are many type of oxygen absorbers available to cover a wide array of applications. These are different brands of different scavengers, oxygen scavengers available. What is inside them? The components of an oxygen absorber vary according to the intended use, the water activity of product being preserved, and other factors. Often the oxygen absorber or scavenger is enclosed in a porous sachet or packet, and they use a mixture of iron powder and sodium chloride. Let me see, there's a question. Okay. Yes, we'll come to this point that the question is how do we know if we need to replace oxygen scavenger or can we reuse oxygen scavengers? We'll just come to this point in the next slides. Often activated carbon is also used. So we have iron powder and, we have iron powder and sodium chloride, or we can have activated carbon. Uh, is also included as it absorbs some other gases and many organic molecules, further preserving the products and removing the odors. Now, properties of oxygen scavengers, they have absorption capacity, reaction rate. Is actually, I won't go into all these details in this particular discussion. Uh, I will come to, and these are the details about the oxygen scavengers. We need to know the oxygen absorbing capacity of them and the volume of the enclosure and the leak rate of oxygen from the outside into. So I'm not discussing these. Here we come to the monitoring part. So monitoring the anoxic conditions. Now, when do we think that there's a lot of oxygen built up inside? There's a huge leakage. So we also keep these small tablet kind of thing, which is basically changes colors with the oxygen level. So these are inexpensive oxygen indicators. These we can also buy from this, what is this online shopping we do with, uh, what is it? Amazon. Amazon. So we can get it from Amazon also, but we have more sophisticated oxygen monitors and analyzers, like you can see in the bottom right picture. So when you see the change in color, it's not very nicely visible in this particular diagram, but here it should be pink and here it should be blue. So when it is completely pink, then that means there's no oxygen, but it changes color. It slowly changes into purplish and then bluish, completely blue tinge as it reacts with the oxygen. So if it turns blue, or even if it turns a purplish, we know that the oxygen scavengers are no more effective, and we need to change them. Yes, yes. Okay, I'll talk about this also. They will generate heat. Yeah, this is interesting. If they are piled up and if there's a lot of oxygen exposed to oxygen, if they're exposed to air, because they react with oxygen and then they absorb oxygen, and if they're piled up together, then they might release heat. That is dangerous. So we have to keep in mind all these things, and then uh, do this process, because what we were doing here is we have taken care of all these things, that if we are using oxygen scavengers, we don't have to pile them up in at one place, and they should not be exposed to some leakage point that they may get in contact with a lot of air, a lot of oxygen. So we have to take a lot of preventive measures if we are using the oxygen scavengers. But if there's a small enclosure and little amount is used very carefully, then they are rather very helpful. So then all these negative points that might come to our mind would not be as important as the preservation aspect. So more monitoring can be done, not just about the oxygen. We have RH monitors, temperature sensors, and leak detectors also. And this is something important. I'm not going into the leak detectors, though I don't know if it is visible to you or not, because no, yeah, it is visible to you. So, because I had removed certain slides from here, because in a 1 hour discussion, I don't think I can go into all the details. Maybe in another webinar or discussion, we can talk about. And you can also send me email so that I can share whatever I know, and the references I have. Mainly, they are the Getty publications and a lot of study from various articles and papers, research work done by different people. So I have been just making notes and studying all these things and applying to my job also. So leak detectors are also can be there. They should be as gas tight as possible, all the Anoxia enclosures. Otherwise, the purpose is defeated. Therefore, testing to find leaks and eliminate them is essential. And the greatest risk of leakage is along seams where they are joined, and including those for windows in aluminized film, because some of the we have I've shown you pictures with the transparent plastic thing, but another layer of aluminum can also be added if you don't think that you need to see the object, because it is very effective. So there are many anoxia treatments which are done with this material, which apart from those 3 to 5 layers, they have a layer of aluminum also. So uh, so leak detectors are also a very important part of this treatment. So there is no leakage, and of course then there won't be any um, damage that we can think of because of oxygen scavengers or oxygen absorbers. That is all for today. This is that picture where have a heat sealing machine. We have that particular plastic material. We have an oxygen scavenger. It is in a porous package, and we have a Y hose. One is connected to the vacuum, other is to the nitrogen cylinder. And we first used to take out all the air. We opened this knob which is connecting to the vacuum, and would create a vacuum, and then we'll close this and we'll open this thing and introduce the nitrogen gas and immediately seal also. Of course, this whole thing there was just one little opening for the pipe, and rest of it was already sealed, and we'll seal uh, a little further from there. We'll seal before taking out that pipe. Just before when we are taking it out, we'll seal it again. So this is how we created these enclosures with nitrogen gas, no oxygen, and we had introduced one indicator, those tablets also. So they now know that because after 2 years, I think, when I visited the place again, some of them They were doing, I just trained them, they were doing it on their own. So some of the sealing wasn't proper, heat sealing wasn't proper, and some of the bags, in some of the bags the indicator tablet had turned blue. So they did it again then, and they knew that what would happen. So because the staff, they didn't know it properly, that what is the importance of all these things. So we had another discussion, and then they did the packaging of that particular material again. So this is how now they are all safe, at least uh, because I visit that place quite, not exactly frequently, but once a year at least. And uh, we are so happy to see that the collection is now very safe. So this is all about, we started from the frames and what are the three different options with frames, then display cases, um, ventilated, passive, active, and then we talked about the storage and individual objects, collection of objects, and the whole shelves, the whole cabinet and all. So now I'll take, so I have answered all these. The two questions I have answered, and you can now unmute oh, and ask. I'll allow to talk. I'll just allow everybody to talk now. So I think I have allowed everybody, almost everybody. Yeah, and I'll go to the gallery view, and I'm stopping the sharing. Stop share. So, so any other question? You can, Amazon, Anjali. Yes, I couldn't see the chat that time. So, Amazon. And materials for oxygen indicators, that I don't know exactly. They are from different brands. It's a good question, and I'll also like to look into it. So any other question answer? There are more questions. Okay, William. Yes, sure. You're asking that I found the research on indoor microbial species really helpful. Is it possible to read about your findings in an article or publication? Yes, sure. Uh, there is one uh, on internet, and one is not yet published. So I'll share with you in a mail. I'll note it down and I'll send you a mail. Rather, I'll share with all of you interested. And another question, would like to Gillian Santiago. I would like to ask, what is acceptable temperature and relative humidity for a tropical country like Philippines? Uh, Ideal temperature and humidity is according to the object, I think. It is not according to where it is. So, and that is why we are creating a microenvironment for it. And for paper, the humidity should be between 40 to 55%. We have talked about the humidity and relative humidity and how it is expressed in percentage in our last webinar. So the temperature can be around 25 degrees Celsius, but and humidity from 40 to 55, not more than that. So whether it is a tropical country or there you might be having more humidity, more heat, which is damaging. So that is why we are creating uh, this microenvironment so that it is according to the object, not to the surrounding or the particular country or place on the planet. So acceptable humidity and temperature is according to the object. 45 to 55% RH. Another question is, sorry, what type of plastic again is used for packaging? It is a food grade plastic. I'm answering alive this one. Uh, so it is a food grade plastic which is used for, which is specially manufactured for the food industry, for packaging the food which can get spoiled otherwise. So, and it has different layers. So it is available in the market not that easily. Mainly the manufacturers who are dealing with an anoxic environment and microenvironment, they might be selling it as a whole with a whole kit. Otherwise, you can also look into the manufacturers for preparing who are manufacturing this plastic, special plastic, food grade plastic for food material. You can find it on, if you search on internet, I think you'll find some manufacturers in the area around you. So I saw long time back when I just started this trying this treatment. I think 10 years back or so. I looked into various manufacturers, searched on internet, and I found some of them in Gujarat. And somehow after many years, I did first work of anoxia treatment in Gujarat only. And then, can you suggest suppliers where? Okay, suppliers right now I don't know, but all the I'll just uh, the brands that are selling um, kits uh, or packages for anoxia. I tried one in US, but somehow I couldn't reach. There was no communication, proper communication, though I had sent many mails. They were keep safe and Glasbahn. They do microclimate, but not the plastic, I don't think. But CTS is, they have this, CTS has got this whole arrangement for anoxia. There are some more. As right now, I don't remember all the names, but there are some more. So, and any other questions? Okay, thank you. Where can you buy the film that you used? Okay, so there were some questions in the chat and some questions in the question answer, and I think that's all. Is there anything else? We can communicate through email also after this webinar is over, and I can send you material and answers in the follow-up emails. So thank you so much for being here, for taking out time. And please let me know if m- some more information is required about this particular topic. We can have a new webinar on this. Thank you so much. So there's another question. Let me see. Research on individual RH. No, I think I've answered all of them. Uh, send. It hasn't. Okay. Send. So I've answered all of them. Okay, that's it. Okay. Thank you so much. Thank you all.